So let's begin with the reactions of acyl halides or acid chlorides specifically. Being the most reactive, acid halides can easily be converted into all other carboxylic acid derivatives by acyl substitution. The idea of this is the following. Whatever group is below this acid chloride will replace it. So meaning that this group right here, let's say you have it, will replace the Cl, the OCH3, the OH, the NH2. So this is the most reactive best leaving group and can be replaced, the leaving group, very easily. So again, general, even less reactive acyl compounds. So, and this is the talking about what we just summarized, can be easily synthesized from more reactive ones, forming a more reactive acyl compound from a less reactive one requires special reagents or forcing conditions. So in this case, what we're trying to say here is that it's very easy to make an anhydride from the acid chloride because it's the most reactive. This is the least reactive. But it's very difficult, or you will need special reagents to make acid chloride from the NH2. So I'll give you an example really quick because we need to show you some examples. So for example, I have this. And I want to go to this. Easy. But if you want to go the other way around, difficult, need the special reagents, or we're just going to say special conditions. So forcing conditions, heat, and generally pressure, in case that applies. So that's what we're trying to say here in this reaction. So let's take a look now at some of its examples of acyl substitutions with acid chlorides. So here we go. We have acid chloride. We have a nucleophile. Let's put the lone pairs on the O. Attacking the carbonyl, breaks the pi bond. So you're adding the nucleophile. That's that step. And what we have now is CH3, Cl, O minus. We still have the Cl. And now look what's added. This whole nucleophile has been added. This one is that right here. So remember, you always have to ask yourself, is this a good leaving group? And it is the best leaving group. So then these can come down and kick Cl out, not the OCOR, because this one comparably is a worse leaving group than Cl. So then the next step is you eliminate. So you have an addition, then an elimination, and then this is your final product. Okay, so if you are unsure, this group right here, I'm going to put it in red, is this group right there. Don't include too many circles because you can confuse yourself, but I'm trying to show you what has been added. So I'm going to delete that, but that's exactly what happened. Of course, you have Cl minus. As well. Same thing now with making an ester. So we have lone pairs on the O. Okay, now pyridine, we've seen that in the aromatics chapter, is a good base. So what pyridine is going to do is act as a base to deprotonate in the next step. So again, you ask yourself, what's a better leaving group, the Cl or the OCH3? Of course, Cl is the best leaving group. So the molecule is smart enough to say, yep, the Cl is out, not the OCH3. Because once again, let's go back here and notice that this is the most reactive because it has the best leaving group. So whatever is below it will replace that Cl. So these electrons are going to come down, kick that out. Now we need to do one more step, and that is to deprotonate. Remember, we don't like to have oxygen with 3 bonds. So that's what the pyridine does. The pyridine, and if we just draw this upside down, and then we finally have, and let me just draw it up here. Our ester. So we made an anhydride. We made an ester. And now we're going to make an amide. So here's an important piece of information. Please be aware of this. We have 2 equivalents or 2 moles. So there's a need for that, as you will see in the mechanism. So the first equivalence is going to act as a nucleophile. right there. Nope, there's no lone pair. There's a positive charge. Oops. Here we go. So remember, needs to be deprotonated, and that's what the second equivalence is going to do. So you can just leave it like that. So this is the first equivalence. And this is what the second equivalence does. It deprotonates. And of course, we'll just do one step at a time. This is going to come down and this leaves. So you have it all in one step. Probably we can break this up into multiple pieces, but I just wanted to streamline this. So you have now this right here. So you made your amide. So again, as we say, an extra equivalent of amine is needed for this reaction so that the first equivalence of the amine that's added as a nucleophile will be protonated. So it will be protonated in this reaction. Therefore, the protonated amine is not nucleophilic. And as we said, also this was in chapter 21 that the reaction will stop at 50% conversion if only one equivalent of the amine is used. So we needed again to attack as a nucleophile and to deprotonate the other or the added amine group. And again, we need to aim at more than 50% conversion. That's the key here. So then another question would be, why not just deprotonate the C with the Cl minus generated in this reaction? So again, we add, and then we're going to again deprotonate using it. You're going to form more of the protonated, and let me draw this here. So again, with this, you're going to have now which is positive. That's the idea. So that's why, again, you need two equivalents because you're going to form more of this and you need more for the nucleophile and the base. So the question then is, why not just deprotonate with Cl minus? Well, that's a problem, and here's why. So suppose we form this intermediate and we get to this step. So you're asking, why can't you just deprotonate with Cl minus? Now the problem is, you probably know this already, is that this is already a weak base. So there's a positive on this. Just put the positive on the end. And you're going to form NHCH3 plus HCl. Now the problem is that this has a pKa of -7. We talked about that. And this has a pKa of around 10. So what happens here, the problem is that if you recall, you always shift toward the weaker side. And this is now a weaker acid than this. This is a strong acid. This is a weaker acid. And if you recall from organic 1, the equilibrium always shifts toward the weaker side. So your equilibrium will be drawn this way. Let me erase this. So the forward reaction will be very small and the reverse reaction would be extremely large. So that's why the reaction doesn't take place. Now, another issue is that even if you generate more, if you even did deprotonate with Cl minus, you will generate HCl, which will react with the amine. So guess what? Now you're going to make more of this. And again, this is not nucleophilic. So that's why you use the two equivalents. That's why you use the two equivalents.